What specific problem does the MOHAWK method aim to solve in the context of language models, and why is addressing this problem significant?
The MOHAWK method aims to address the inefficiencies associated with the quadratic self-attention mechanism in transformer architectures by facilitating the distillation of subquadratic state space models, SSMs, from pre-trained transformers. This is significant because it allows for the development of models that maintain competitive performance while drastically reducing the computational costs associated with training and inference, as evidenced by the Phi Mamba model achieving strong benchmark results with only 3 billion tokens, less than 1% of the data used for training top-performing models. The three-phase distillation process, comprising matrix orientation, hidden state alignment, and weight transfer, ensures that the student model effectively learns from the teacher model, thereby enhancing its performance without the need for extensive training resources. By leveraging the vast resources already invested in training transformers, MOHAWK demonstrates that it is possible to create efficient models that can outperform previous subquadratic models, highlighting the potential for more accessible and scalable language model development. This approach not only improves model efficiency, but also contributes to the broader goal of making advanced language processing capabilities more widely available.
How does the proposed MOHAWK method work? Please illustrate the step-by-step process of the three-phase distillation: matrix orientation, hidden state alignment, and weight transfer and knowledge distillation.
The MOHAWK method consists of a three-phase distillation process designed to train subquadratic state space models, SSMs, by leveraging a pre-trained transformer model. 1. Matrix orientation. In this initial phase, the student model's matrix mixer is aligned with the teacher model's self-attention matrix. This involves setting the components preceding the matrix mixer in the student model to match those of the teacher, followed by minimizing the distance between the two matrix mixers across all layers. 2. Hidden state alignment. The second phase focuses on aligning the hidden state outputs of the student and teacher blocks. This is achieved by minimizing the L2 norm of the outputs from the student's Mamba block and the teacher's self-attention block, ensuring that the student model learns to replicate the teacher's output distributions effectively. 3. Weight transfer and knowledge distillation. The final phase fine-tunes the student model by transferring the remaining weights from the teacher model to the student's components, such as token embeddings and MLP layers. This phase employs a distillation loss to encourage the student model to mimic the teacher's logits, effectively integrating the knowledge from the teacher model into the student model while maintaining performance. Together, these phases enable the Phi Mamba model to achieve strong performance with significantly less training data compared to traditional methods.
Can you provide a simple yet illustrative example of how the MOHAWK method operates during the matrix orientation phase? Walk through the example, explaining how it aligns the sequence transformation matrices of the student and teacher models.
In the matrix orientation phase of the MOHAWK method, the goal is to align the sequence transformation matrices of the student model, Phi Mamba, with those of the teacher model, PHI1. 5. For instance, consider a specific layer in both models where the teacher's self-attention matrix is denoted as A_teacher, and the student's matrix mixer is A_student. The first step involves setting the components of the student model preceding the matrix mixer to match those of the teacher model, ensuring that the input to the matrix mixer is identical in both models. Subsequently, the method minimizes the distance between the two matrices, A_teacher and A_student, by applying gradient descent to adjust A_student, so that it closely approximates A_teacher. This alignment process is crucial as it ensures that the student model's mixing layers are effectively trained to replicate the transformations applied by the teacher model, setting a solid foundation for the subsequent phases of the distillation process.
What are the theoretical or practical advantages of using the MOHAWK method over traditional training methods for transformers and other subquadratic models?
The MOHAWK method offers several theoretical and practical advantages over traditional training methods for transformers and subquadratic models. Firstly, it employs a three-phase distillation process that includes matrix orientation, hidden state alignment, and weight transfer, which allows for a more structured and efficient transfer of knowledge from a pre-trained transformer to a subquadratic model like Mamba-2. This structured approach enables the Phi-Mamba model to achieve superior performance on benchmarks with significantly less training data, only 3 billion tokens compared to the 315 billion tokens used for other models, demonstrating its efficiency in resource utilization. Additionally, the method allows for the retention of learned representations from the teacher model, which is crucial for maintaining performance while reducing the number of parameters and training costs. Empirical results show that the MOHAWK method leads to better downstream performance and lower hidden state distances, indicating a more effective learning process compared to traditional methods that often rely solely on end-to-end distillation. Overall, MOHAWK not only enhances the performance of subquadratic models, but also makes them more accessible for practical applications by reducing the computational burden associated with training.
How was the MOHAWK method validated or tested? Discuss the experimental design, datasets used, and performance metrics that demonstrate its effectiveness.
The MOHAWK method was validated through a series of empirical evaluations involving the Phi-Mamba and hybrid Phi-Mamba models, which were distilled from the PHI-1. 5 model. The experimental design included distilling these models on a total of 3 billion tokens from the C4 dataset, with specific token allocations for each of the 3 stages of the MOHAWK process: 80 million for stage 1, 160 million for stage 2 and 2, 76 billion for stage 3. Performance metrics were assessed on various downstream benchmarks, including Winogrande, HeliSwag, PIQA, and ARC datasets, where the Phi-Mamba model achieved notable accuracy improvements, such as 71.7% on the Winogrande dataset, compared to the pre-trained Mamba-2 model's 60.9%. Additionally, the hybrid Phi-Mamba model demonstrated competitive performance, closely approaching the pure attention transformer architecture while utilizing fewer parameters and attention layers. The results indicated that the MOHAWK method effectively enhances model performance while significantly reducing the training data requirements compared to existing models.
What limitations or drawbacks were identified in the MOHAWK approach, especially in relation to the performance of the Phi-Mamba model compared to larger or more complex models?
The MOHAWK approach, while effective in distilling the Phi-Mamba model, has limitations in performance compared to larger or more complex models like PHI-1. 5. Specifically, the Phi-Mamba model, despite achieving strong results, still lags behind the base PHI-1. 5 model on benchmarks, indicating that it does not fully capture the performance capabilities of the larger model. Additionally, the hybrid Phi-Mamba, which retains some attention layers, only closely approaches the performance of the pure attention transformer architecture, suggesting that the integration of attention mechanisms is crucial for optimal performance. Furthermore, the experiments revealed that while the Mamba-2 sequence transformation can approximate self-attention matrices, it does not achieve the same level of expressiveness, which may limit its effectiveness in complex tasks. Lastly, the findings indicate that the performance of the Phi-Mamba model is sensitive to the number of attention layers retained, highlighting a potential drawback in relying solely on subquadratic models for tasks that benefit from richer attention mechanisms.